there's a lot going on in photosynthesis, and although I had, in theory, a minor in plant physiology, I won't pretend to remember the stuff well enough to go through all of the reactions. The net reaction of photosynthesis is this. Take 6 carbon dioxide molecules and 6 water molecules and make one molecule, of a 6-carbon sugar and evolve 6 oxygens. That is the net reaction of photosynthesis. The details are much, much more complex. There are specialized photosynthetic pigments which the photons strike and energize, if you will. The high energy electrons that are produced in those capture events then flow through a complex network of proteins to eventually form adenosine triphosphate and NADPH2. Don't ask me to remember nicotine, whatever, sorry. This photon capture and the electron transfer up to the formation of ATP and NADPH2 are called light reactions. They happen in the light. ATP and NADPH2 are energy carriers that are common, I believe, to all cells. In photosynthetic cells, they're generated by the capture of photons. In photosynthetic cells also, and in other cells that are non-photosynthetic, ATP and NADPH2 are generated by the reverse reaction, the respiration reactions of sugar and oxygen going back to carbon dioxide and water. You with me? The actual manufacturing, stitching together of sugar from these low energy compounds uses up these high energy intermediates. Okay, so ATP and NADPH2 are used to synthesize carbohydrates. And interestingly, that reaction can actually take place in the dark. And in some plants does, CAM plants. But generally, it takes place at the same time during the day. But it is known, because it can, in theory, take place in the dark, it is known as the dark reaction. So you have the so-called light reactions and dark reactions. So 3 steps, right? Absorption by a pigment, transfer of energized photons, or conversion of energized electrons, pardon me, into intermediates, ATP and NADPH2, and then consumption of NADPH2 and ATP to manufacture carbohydrates. My apologies to all the biochemists out there for my gross oversimplification. The maximum efficiencies of photosynthesis are relatively low. Bolton and Hall did an analysis and suggest that photosynthesis cannot be more than 13% efficient on a total incident radiation basis. And if you instead say, no, how about on a photosynthetically active radiation basis, they argue that it's about 30% efficient maximally. Absolute theoretical maximum. They go a step further and say, if you look at some of the other losses that you know are going to be there, the fact that light is not going to be absorbed completely, the fact that some light will be absorbed by non-active pigments, the fact that photorespiration can occur where essentially the system starts to short circuit itself at high light intensities. When you take those into account, you drop to a 9% overall efficiency, or 21% maximum on a PAR basis. Okay, so it depends on what you use as a denominator. But I think these are good numbers. I think that having the 9% on a total irradiation, maybe most importantly, 21% on PAR is a good number to have in your mind. If somebody tells you that they're above that, they better be a really good plant scientist who understands how they're getting around it, or a photosynthetic scientist, or you need to call their bluff. All right? Now, what are the implications of these low efficiencies? Let's do the same problem. Let's assume that we get 600 watts per square meter. We'll use a total incident radiation number. And let's say that we can't get the 9% cap. Let's say we get the 4.5% cap. Again, what's the land rent only cost of this energy? And I'm going to work the same problem the same way. I'm going to say I can capture that 600 watts per square meter, 3,600 seconds per hour, 10 hours per day, 120 days per season. And I'm going to capture at 0.045 efficiency. And I can capture 117 megajoules per square meter. The energy captured then per unit area is simply that 117 megajoules per square meter, I'm sorry, energy captured per acre, times my conversion, 47 square meters per acre. So I am up to about 470 gigajoules per acre. All right, and my land rent only cost then is equal to $150 per acre over my 470 gigajoules per acre, and I get that as about 32 cents per gigajoule. Once again, I have not counted the cost of growing the crop, harvesting the crop. I've not counted the fact that even if this crop actually captured this photosynthetically active, or I'm sorry, this radiation at 4.5%, I wouldn't access all the energy that had been captured, right? Because some of that crop is underground and I'm not going to harvest that. But I think it's an interesting number. I think it's an interesting number that gives you some idea, again, why maybe, just maybe, some of the biomass to energy schemes have the potential to be economically competitive. What I mean to say is that there's a bound out there that is set by some theoretical considerations. And if when we went through this calculation, we found that there's no way that you could get energy cheaper than $20 per gigajoule. Let's say that was the end point. Let's say when we ran these numbers, we ended up going, you know, 20 bucks per gigajoule is the best you can do. I honestly think that if that were the case and energy costs what it does right now, that a lot of us would say, hold on, you know, chasing after biomass as some kind of feedstock for any part of our energy is ridiculous, because even under some of the more optimistic assumptions that we've made right here, the costs are not at all competitive. So what I want to say to you, I'm not saying that 10 years from now we're going to get we're going to make energy for practically an eighth of what we make it today from coal using biomass. I'm not saying that. But what I'm saying is that if you look at where the bounds are, the bounds suggest that there's some interesting space into which we can move. All right?